All right. So we're going to go ahead and get started now. So we are now trying to address full force the question of whether there's life elsewhere in the universe. We're going to start today answering the part of that question that we have solid answers to, which is the discovery of planets outside of our own solar system, and in particular, the recognition that planets like our Earth, similar size, similar temperature, similar likelihood of having water, are actually quite common. And then the last few lectures will try to address the more difficult parts of this question, like what is the likelihood that there's actually technologically advanced life as opposed to fungus and bacteria on these other planets. So what we're going to talk about today in particular is how do we detect planets around other stars? What do we learn using the different techniques? Given the planets that we have detected, what are the properties of other planetary systems that we found? And then how common do we think habitable planets are? Where I put habitable in quotes because we've learned now through Mars, the moons of Jupiter, the moons of Saturn, that our notion of what habitable is probably a little bit restricted. So I'll explain exactly what I mean at the end. So I want to start by asking you a question just to get a feel for what you think before we get into this. So roughly how many planets around other stars do you think have been detected? We've been searching for planets around other stars, well, actually since the ancient astronomers, but that search has really begun in earnest in the last 20, 30 years. So do you think we've found 3, 30, 300, or 3,000 planets around other stars? So this is more of a less of a reason it out, although if you can reason it out, great. But it's more of just a gut instinct before we get started. So raise your hand or your piece of paper if you think it's 3, 30, 300. Okay. Some 3,000. Yeah, that's right. That's closer to the right answer. 20 years ago, actually, let me make sure this is right. Yes, 20 years ago, the answer would have been a few, 2 or 3, and they were only planets around neutron stars, not normal stars. So we knew of no planets around stars like our own about 20 years ago, and now the number is in the thousands. So what I want to start by doing is just taking you through some of the different techniques that have been used to actually detect planets around other stars and what we learned from these different techniques. So the first technique that I'm going to highlight, which is also historically the most important one, is directly watching the motion of a star as it moves under the gravitational pull of a surrounding planet. So the planet's gravity causes the star to move, just like the star's gravity causes the planet to move. Even if you can't see the planet, if you can watch the star move, you can infer the presence of the planet from the motion of the star. And the way we do that in practice is by measuring the Doppler shift in the light of the star as the star moves back and forth around in its orbit due to the gravitational tug of the planet. That leads to this periodic Doppler shifting in the light from the star. Sometimes the light is redshifted as it's going away. As the star happens to be moving towards us, the lines in the light of the star are blue shifted, then red shifted, then blue shifted, then red shifted, blue shifted, back and forth as the star moves around under the gravitational pull of the planet. By measuring the change in the wavelength of the light from the star, we can measure the speed of the star. That's the standard Doppler shift expression that we use to work out, or really Hubble used to work out, the expansion history of the universe using the Doppler shift in the spectrum of stars in distant galaxies, we can use the same thing to measure the motions of stars orbited by planets. And then the idea is once you know the speed of the planet, you can use, the speed of the star in its orbit due to the planet, you can use Newton's theory of gravity to work out how massive the planet is that's tugging on the star, much like we use the motions of things in the solar system to figure out the mass of the sun, the mass of Jupiter, etc. This is actually the first planet that was detected around a star like the sun in the early 1990s. So what this shows is a plot of the orbital speed of the star in its orbit due to the pull of the planet as a function of time. And so there's blue shift, red shift, blue shift, red shift, back and forth as the star orbits around due to the pull of the planet. And again, the reason that we're seeing the star, not the planet, is that the star is enormously brighter than the planet, which makes it extraordinarily difficult to actually see the light from the planet. But you can infer the planet from its effect on the motion of the star. And that's what this allows us to do. So what you can figure out from observations like this is you can figure out the period, how long it takes the planet to go around the star. That's how long it takes this curve to repeat. So in this case, that period is just 4 days. So this is amazing, right? This is a planet orbiting its star with an orbital period of 4 days. The closest planet to the sun in the solar system is Mercury. Mercury has an orbital period of something like 100 days. So this planet is much, much, much closer to its host star than any of the planets in the solar system. And that's one of the big surprises that we'll come back to in a little bit. The other thing that you can infer from observations like this is that the star is moving at a speed of about 50 meters a second due to the gravitational pull of the planet. So again, the star is orbiting around and around and around at a speed of about 50 meters a second. And from that speed, we can actually figure out the mass of the planet that's tugging on the star. And that mass turns out to be about half the mass of Jupiter in this case. There's a little bit of a geometric ambiguity. If you remember the Doppler shift only tells you about the speed along the line of sight. Okay, it doesn't give you the full three-dimensional speed. So there's a little bit of a geometric ambiguity about the orientation of the orbit of the planet along our line of sight. So we don't know exactly the mass of the planet, but we know it to a factor of few accuracy. And so we can directly infer from this the mass and the orbital period of the planet orbiting this star without seeing the planet at all, just seeing the motion of the star induced by the planet. Okay? There's nothing special about other stars. Remember, our own sun does this. We talked about this when we talked about the gravity of the solar system, that the gravity of all of the planets in the solar system causes the sun to move around at the center of the solar system. This shows the motion of the sun at the center of the solar system from 1960 projected into the future, 2020, and the sun is moving around due to the gravitational tug of all of the planets in the solar system. So a natural question is, in our solar system, if we were looking from far away at the motion of the sun like this, which planets would we be able to detect? And so this gives you a feel for how good this technique is and what planets you can actually detect with this technique. So the Earth moves around the sun with an orbital period of about a year. So you need to wait a year to see this pattern repeat. Okay, that's not too long. A year we can wait. The problem in the case of the Earth is that the Earth is so small that it only pulls on the sun with a speed of about 1/10 of a meter per second, and that's below the capability of current telescopes to actually detect. So it would be challenging and, in fact, very, very difficult with current techniques to directly detect the Earth in an Earth-like orbit. So I'll talk about how we try to infer the presence of Earth-like planets, but the challenge is that the Earth's gravity is pretty puny, so it doesn't produce a big speed in the sun. Jupiter is further away, but it's so much more massive that its gravity produces a pull of about 10 meters a second on the sun, and that we can actually detect. The problem in the case of Jupiter is that Jupiter's orbital period is about 12 years, and so you have to wait a while, 12 years or really 24 years. You kind of want to see this pattern repeat a couple of times before you believe it. And so the challenge in the case of Jupiter is you just have to wait a while. Saturn, in principle, we could detect. Current telescopes can detect speeds of a few meters a second, but you have to wait about 30 years for that pattern to repeat, and that's getting to be a pretty long time, the life of an astronomer. And so that's really the challenge for something like Saturn, is just it's so far away, it takes it a long time for this pattern of Doppler shifts, blue shift, red shift, blue shift, red shift, to repeat. So that's kind of a sense of what this technique is good for. It's better for big planets, and it's better actually for close-in planets because those orbit more quickly. With this Doppler shift technique, watching the planet pull on the star, you can measure the orbital period of the planet. You can measure the mass of the planet up to some geometric ambiguity. You can measure the distance between the star and the planet, knowing the orbital period. You can measure the eccentricity of the orbit, whether it's circular or eccentric. So the exact shape of this curve depends on whether the orbit is circular or eccentric. Can you guess by looking at this whether you think this orbit is circular or eccentric? Any guess? So why? Yeah, so first of all, there's a clue. It's kind of E is very close to 0. That means it's circular. But I think the argument a couple of people up front were giving is that if it's eccentric, that means sometimes things are going faster and sometimes things are going slower in the orbit. This looks like it's the same on both sides of the orbit, and so that means it's relatively circular. That's exactly the right reason. Okay. So the second technique I want to describe to you for detecting planets around other stars is the technique called transits. And the idea is nicely illustrated in this animation. If a planet in its orbit happens to pass directly between us and the star, as the planet goes in front of the star, it dims the light of the star by a small amount, as illustrated here. The planet blocks some of the light of the star. And so again, if you're looking at the light of the star, in this case, you infer the presence of the planet by the very slight dimming as the planet passes in front of the star. That's the basic technique. Very simple, blocking the light of the star. With this technique, you can directly measure the size of the planet. And the reason is that the amount of dimming depends on the size of the planet, the area of the planet, divided by the area of the star. And so you get a direct measurement by measuring the amount of dimming. You get a direct measurement of the radius of the planet or the size of the planet. So this technique is extremely good at measuring sizes of planets. Again, you can measure orbital period based on how long it takes this pattern of dimming to repeat. You can measure the period of the planet in its orbit around the star. This technique is generally not as good as measuring planet mass. What you're sensitive to is planet size rather than planet mass in most cases. This is a beautiful example of this technique in action, actually in our own solar system. This is Venus passing in front of the sun. So as Venus orbits around, occasionally, it doesn't happen actually very often, but occasionally Venus happens to pass exactly between the Earth and the sun. And in that case, Venus dims the light of the sun a little bit. And this is a series of images of Venus passing over a period of a few hours in front of the surface of the sun, dimming the light from the sun. Again, illustrating the basic idea of this technique. Yep. Sorry, yes. Yeah, so good question. So what are the limitations of this technique? So there's a couple of limitations. First of all, there's a limitation that if the planet is too small, then it doesn't block very much light of the star, and so it's hard to see the dimming. And that turns out to limit us to planets that are about the size of the Earth or bigger. And so that's the practical limit. There's another more severe geometric limit than in the Doppler shift technique, which is that if you're looking at random stars, their planets are, on average, not going to be orbiting exactly in the plane along our line of sight. So most planets are actually hard to see by this technique. You only see the ones that happen by chance to be orbiting exactly in the plane along our line of sight to the star. So you can't detect most planets by this technique, but you can actually detect many, in fact, thousands, as it turns out to be the case. We've now detected thousands of planets by this technique. So the real revolution in detecting planets by this transit technique was with the Kepler telescope, which was launched in 2009. The Kepler telescope had a very simple task that it did extraordinarily well. It looked at one part of the sky over and over and over and over for several years. That's all it did. Stared at exactly the same part of the sky, looking at millions of stars and measuring very accurately the amount of light coming from those stars, looking for tiny dimmings in the light of the star. And it's hard to overemphasize to you how excited astronomers became by the discoveries of the Kepler telescope. So to convey that to you, I want to show you a video clip of one of my colleagues and the kind of poetic license he went to in describing the Kepler planet.
Smell the planet crossing in front of the star. Smell the planet crossing in front of the star.
So this is my colleague Jeff Marcy talking about some of the discoveries of the Kepler telescope and trying to convey his enthusiasm by somehow invoking, I could just let this go forever, the smell of the planet crossing in front of the star. So geologists, you may have learned in section. If not, you should ask your GSIs in the last section. Geologists, one of the ways that they study rocks is actually by tasting them. I'm not kidding. And astronomers, it turns out, smell planets. So I wanted to show you some of the real data from the Kepler telescope because this really has been quite phenomenal. Just to give you a feel of what the real data looks like and the kinds of planets we can discover with it. So this is one star of the many that Kepler has been studying. This is the brightness of the star as a function of time in days. And 1 here is the average brightness of the star over this period of time. So you'll notice a few things. You'll notice that there's a kind of some scatter It's not exactly 1 on average. There's some variation about 1. And that's partially due to measurement uncertainty and partially due to the fact that because of things like convection, the surfaces of stars aren't perfectly uniform. They vary a little bit. But you'll also notice, I hope, these very dramatic dimmings, where dramatic means the flux goes down to 0.9995, meaning less than 0.1% changes in brightness. But you can clearly see these sharp dimmings. And those actually are a signature of a planet orbiting around the star. This is a planet that has a period of about 45 days. So every 45 days, the planet passes in front of the star. It blocks just a little bit of the light of the star, producing this periodic dimming. So that's an example of one of the planets detected by Kepler. I'm now going to zoom in on this region right here. So this is a zoom in now. This is, not quite a year. So I'm now zooming in to a period of just about 10 days. So we've zoomed in time. There is that drop due to the planet passing in front of the star. And here is the zoomed in brightness of the planet as a function of time. So again, you see those changes due to noise in the instrument and noise in the star. But you'll also now see that there's a second strong dip, which is actually due to a second planet. So the red lines mark the time where the second planet has passed in front of the star. This planet has an orbital period of less than a day. So again, let me remind you, in the solar system, there's nothing inside something like 100 days. Here we have one planet at 45 days and another planet with an orbital period of less than a day. So I can show you this kind of more clearly by averaging all these dips and producing an average brightness as a function of time. Yep? The planet is orbiting very, very, very close to its host star. So the planet is, unlike the planets in the solar system, which are relatively far away, this planet is extraordinarily close to its host star. So the stronger gravitational pull of the star causes it to go around really fast.
I think the question is, in a sense, why is there nothing between Mercury and the Sun? Is it a function of the fact that the size of the star influence how fast you can get things to the star?
Got it. So good question. So why does this planetary system have planets close in when ours doesn't? I think the honest answer is that we don't really know, and this is what Kepler is teaching us, is the remarkable diversity in planetary systems. And we'll come back to that in a second, and I'll give you one example of how we think it is planets may end up so close to their host star. So I'll come back to that in just a second. Great question. So now what I'm going to do is just average together all these little dips. You can see it more clearly. It's actually quite striking. So this is now brightness as a function of time, where 0 is now when the planet is exactly in the middle of the star passing in front of it. And so you can very clearly see this little dip. By this dip in brightness, which is 0.01% dip in the brightness of the star, we can measure that this planet actually has basically the size of the Earth. This planet orbiting around this star has a size of about 1.4 times the size of the Earth. It's probably not a very hospitable planet because it's orbiting so close to the star that it's incredibly hot. And I'll come back to that in just a second. So what we know from this observation is the direct detection of a planet with a size similar to the size of the Earth. What we don't know actually from this alone is what this planet is made of. It turns out you can have planets the size of the Earth that are either mostly rock, so they're solid, or they're mostly water, so they're liquid. And with this measurement alone, we can't distinguish between a mostly rocky planet and a mostly liquid planet. And the reason is that the fundamental distinction between water planets and rocky planets is their density. Rock is denser than water. That's why if you drop a rock in a pond, it sinks. Rocks are denser than liquid. And so to figure out what the planet is actually made of, we need to figure out the density of the planet, which means we need to measure not just its radius, but also its mass. And the problem with this transit technique is the transit gives us very accurately the size of the planet from the dimming, but it doesn't give us the mass of the planet. And so the way we can figure out which of these it is by combining our two techniques. We can use the information from the Doppler shift of the stellar light to figure out the mass, and the transits give us the radius. Combining the two techniques, in this particular case, we actually know that this planet is mostly rock. If it has any water, it's a very small amount of water. And that's because the density of this planet is very similar to the density of rock, not the density of water. Now, this is a very odd rocky planet. It's orbiting so close to its star that the side of the planet facing the star has a temperature of about 2,500 degrees centigrade. So that's incredibly hot. Water would completely boil, right? There wouldn't be liquid water in the first place. But this planet, like the moon, is tidally locked to its host star. So this side of the planet always faces the star. So one side of the planet has a temperature of 2,500 degrees. The other side of the planet doesn't get any sunlight, or starlight, I guess. So its temperature is about minus 200 degrees. So this is unlike any planet in the solar system in the sense that one side is probably incredibly cold, possibly icy. The other is incredibly hot with any liquid water completely having evaporated away. Yep. Good question. So how do we measure the temperature? What I'm telling you here is our best guess of the temperature, knowing the distance from the star. But you're right, these are not measured quantities. These are actually theoretically inferred quantities given other things we know about the system. Good question. Yep? Yeah, so the question is, all right, 2,500 degrees centigrade minus 200 degrees centigrade. What about right there? Maybe that's, a nice kind of tropical condition with some thunderstorms. That's a great question. So we don't know if there's much of an atmosphere. It may be so close to the star that the atmosphere has been completely boiled off and baked off. So exactly how the temperature changes as you go from here to here is a very hard question to answer. We don't have a good understanding of that right now. This is, again, something that people are really actively working on. So great question. Is there another? So another great question. So what if it has a tilt in its rotation? It almost certainly doesn't have a tilt in its rotation because tides, just like they make the same face of the planet face the star, they also kind of get rid of the axial tilt, we think. So it almost certainly doesn't have an axial tilt, but that's a theoretical prejudice, not an actual measurement. So good question. There are a few planets where we've actually started to measure differences in the day side and night side temperature. I'm not going to go into that. There are ways you can actually start to measure that. So that's kind of one of the frontiers, is trying to measure these differences in temperature. Okay. Any other questions? Okay. So the third technique I want to briefly mention, transits and Doppler shift, are the two major techniques that we have used to detect planets around other stars. There are two other techniques that are growing in importance, so I want to briefly mention them. One of them is this technique of gravitational lensing. So we talked about the fact that if you look at the light from a distant star and another star happens to pass between us and that distant star, then the light of the distant star is lensed by the gravity of the intervening star. That lensing actually produces a brightening in time of the light from the star. So this is in some ways the opposite of a transit. In this case, the star, as it passes along the line of sight, isn't blocking the light from the distant star. Instead, its gravity, through the action of lensing, is actually leading to a brightening in the light of the distant star. And the amazing thing is that if that distant star, if the star that's acting as the lens, I said that wrong initially, so if this star, the lens, has a planet orbiting around it, as illustrated here, so this is us, distant star that's being lensed, star along the line of sight producing the lens. If that star has a planet, that produces a little blip, a sharp spike in brightness as a function of time, due to the presence of the lensing by the planet. So this is kind of a very subtle effect, that the gravity of the planet changes the strength of this lensing effect and produces its own little brightening of the distant star. And this has actually been detected in about a dozen or so cases now. We have discovered planets through this technique. The nice thing about this technique is that you can actually detect planets like the Earth or Jupiter. For reasons I'm not going to go into, you're actually more sensitive to relatively distant planets, planets at the distance of Jupiter, Saturn, and the Earth, and you can detect even very small planets with masses like the mass of the Earth. And so there is a lot of interest in this technique because it can allow us to actually find Earth-like planets in Earth-like orbits. Yep? So what is doing the lensing is the gravity of both the star. The gravity of the star causes this overall brightening over about a month. This is time in days. The brightening of this distant star, the light from this star gets brighter and then fades away as this star passes along the line of sight between us and the distant star. And then, go ahead.
So the first peak you say when the star is in between the source star and the detector, and then the little blip is when the planet goes in between?
Yeah, that's right. So this peak is when the star is about along the line of sight. The second peak is when the planet is about along the line of sight. And so the planet produces this very short, about a few hours long, little blip. Okay. And so, in some ways, the details of how this lensing works aren't critical. The point I want to emphasize to you again is this is the power of this lensing technique. We've talked about how lensing allows us to study dark matter, how it allows us to study black holes in our galaxy, and now how it allows us to find planets orbiting around distant stars. So the last technique I want to mention is in some ways the technique you first think of when you think about trying to find planets around distant stars, which is actually just seeing light from the planet. So this is a picture of the night sky. I've shown this one before. This is lots and lots of stars in a small little patch of our Milky Way galaxy. And in this picture, I guarantee you that there are actually hundreds, if not thousands, of planets around the stars in this picture, but none of them can you see with your eye. And the reason is that the light from the planets orbiting the stars is so faint that it's extraordinarily difficult to see. The light from the planet is dwarfed by the light from the star. So it's extremely challenging to directly see the light from the planet, but this is just now, really in the last 4 or 5 years, become feasible. And so I want to describe a little bit how that works. So the basic idea is the following. So imagine this is a distant star, not the sun, but some other distant star. We're sitting here on a nice mountain in Hawaii, on our nice 10-meter telescope, trying to find a planet orbiting around this star. The way we could do that is that light from the star travels towards the planet, and it's reflected off of the planet, and it comes to us. That's one way we could see this planet, is that it reflects some of the visible light produced by this star. The challenge is that the Earth only reflects about 1/1000th of the light produced by the sun. So the amount of reflected light going off kind of into space because of reflection of sunlight from the Earth is only about 1/1000th of the luminosity of the sun. And so that's the challenge, is how do you see that tiny amount of light that's only about 1/1000th of the total light produced by the sun. So this isn't the only way that you can directly see the planet. The other way you can see the planet is not by looking at reflected light in the visible, but is actually by looking at thermal radiation, thermal infrared radiation. So remember, planets, because of their temperature, produce their thermal blackbody radiation, not in the visible, but in the infrared part of the electromagnetic spectrum. You talked about this again when talking about the greenhouse effect in section last week. And so, for instance, Jupiter, this is actually a picture of the thermal radiation from Jupiter. Jupiter has a luminosity in the infrared due to its thermal radiation, which is about 1,000,000,000 times smaller than the sun. So if you can see in the infrared the thermal radiation of the planet, that's another way to directly detect light from the planet. So you can detect light from the planet either by looking at reflected visible light from the star or by looking at thermal radiation in the infrared. Either of these is incredibly challenging because the planet is so faint compared to the extraordinarily bright star. The basic idea of how you see this very faint planet in the face of its extraordinarily bright host star is that you block the light from the star. And this technique is called coronagraphy, or a coronagraph. It's illustrated here in this image of the sun. So the sun is behind this black disk. This black disk is a coronagraph that's blocking all of the starlight from the sun, except the tiny amount of starlight that travels out and is reflected in the corona of the sun is scattered in the corona to us here on Earth. And so the way we detect planets around other stars is very similar to this. The way we directly see the light from planets is you try as hard as you can to block the light from the star so you can see a very faint orbiting planet around the star. That's the basic idea. And then the name of the game is how well can you actually block the light from the star. And this is a real technical challenge. It requires an extraordinary amount of careful design of telescopes and instruments, but it's now been done. So this is an example of one of the first directly image planetary systems around another star. The star is at the center here. This, and this. Okay, these are all planets orbiting around this star. There's all this junk in the image that you see, this kind of ring and this weird little thing here. That's all artifacts in the image that have to do, so those aren't real. Those are artifacts in the image, complications associated with what happens if you try to very carefully block the light from the star. It produces a kind of ringing pattern that's in some ways similar to what happens if you throw a rock in water. You get that kind of ripple of waves going out. When you block the starlight, you get a kind of ripply pattern in the image. And that's what you're seeing here. But this thing, these points here with the arrows, are actually real planets orbiting around this star. And in this case, we are directly seeing the thermal radiation from the planets. You'll notice the scale bar here. This is 20 astronomical units. So to remind you, the Earth orbits 1 astronomical unit from the sun. That's the definition of an astronomical unit. These planets are orbiting quite far from their host star. And the reason is because those are the planets that it's most easy to see. It's very hard to see by this technique planets that are very close to their host star because those get lost in all these artifacts of the image. So the planets that you can detect the most easily are relatively distant planets, and also, it turns out, relatively massive planets. Massive planets are physically bigger, so they reflect more starlight, and they're also brighter. Massive planets have more thermal radiation, and so they're brighter. So these planets are actually all more massive than Jupiter in this particular system. One of the reasons there's so much interest in this technique is that if you're directly seeing light from the planet, then just like we use the light from stars to figure out what the atmospheres of stars are made of, is it hydrogen or helium or carbon, oxygen, iron, whatever, because you're directly detecting light from the atmospheres of planets with this technique, you can actually measure what the atmosphere is made of. And so this provides a way of starting to get at questions like, does the planet actually have an atmosphere? Does it have an atmosphere of oxygen? Does it show evidence for water vapor in the atmosphere of the planet? Really interesting questions that get at habitability become easier to answer directly if you can see the light from the planet. So the other planetary system, the other system that was one of the first directly imaged planetary systems, is this system here. This is the star. All of these streaks, a lot of these streaks here, or essentially all of these streaks really, are again artifacts in the image having to do with how the light from the star was masked or blocked. The planet, we think, is this little bright spot right there. And there's a zoom in here. That's the bright spot. And they've actually watched the motion of that bright spot over something like 10 years now and watched it orbit around the star. And so in this case, you're actually watching the motion of the planet in its orbit. And you can see one of the reasons that this is such a challenging measurement to do is you have to convince yourself that this bright spot is real and not an artifact of, again, the difficulty of blocking the light from the star. This particular system has generated a tremendous amount of interest in the press. This was on the cover of many newspapers and magazines when the discovery was announced. And I honestly don't think that was for scientific reasons. I think there was a different reason this generated so much interest. And that's because this looks an awful lot like the image from The Lord of the Rings of the Eye of Sauron. And that's the connection, all the newspaper articles and magazine articles that had this image, they kind of started the article off by talking about Middle-earth and stuff like that. This was actually done by a colleague of mine here, James Graham and Paul Callis in the Astronomy department. Okay, so we've talked now about 4 different techniques for measuring planets: Doppler shift, transits, gravitational microlensing, directly seeing the light from the planet. These different techniques are sensitive to different types of planets. Some of them favor close-in planets. Some of them favor distant planets. They give us different information. Doppler shift gives us accurate masses, but it doesn't give us information about the radius. Transits gives us radius, but much less information about the mass. Direct imaging gives us atmospheres, etc. And so I hope you can see that by combining all of these techniques, we can really start to build together a census of the types of planetary systems that there are. And so that's what I want to turn to now, is really aggregating the information that we've learned from all of these techniques over the last 20 years or so to infer what are the properties of planetary systems around other stars. And I think the first key take-home point, and really in many ways the most important take-home point from what we've learned, is that planets are extraordinarily common. On average, there's probably at least one planet for every star in our galaxy. That's what we've learned by studying these different techniques of measuring planets around other stars, is that there are planets around almost every star we look at, statistically, seems to have a planet orbiting around it. This is an artist's conception trying to convey that fact. You see a bunch of stars with their planets orbiting around them, and many, many, many of the stars in this image have little circles representing planets in orbit around the star. This is actually a very bad artist's conception. It's extraordinarily misleading. Why is this misleading? It's misleading actually for many, many, many reasons. So give me one example of why it's misleading. Yep. Yeah, in particular, in this picture, it looks like the star has a size which isn't all that different from the distance to the nearest star, and that's definitely not true. Okay, that's a problem. There's another problem. Yep. Yeah, the planets also look pretty big compared to the host star. That's not realistic. There's another problem. So I think the worry was that they're all orbiting in the same way. I think they are trying to convey different directions of orbits. Like this one is orbiting in a slightly different direction than this one. The other problem is that the orbits of the planets are really big. Basically, they have the planets orbiting out to distances comparable to the distances to nearby stars. That may be true in some cases, probably isn't true in most cases. Certainly isn't true for the planets that we've actually detected.
Well, the other way of looking at it is that they're really small because they're close compared to the radius of the star.
Yes.
Yeah.
Yes. So this is an attempt to convey the fact that there are many, many planets. It does convey that, but at the expense of being wrong. Okay. One of the other, I think, really amazing discoveries in searching for planets around other stars has been the discovery that there are actually many planets that aren't orbiting stars. There are many planets that are just freely floating out there, not actually orbiting around a star. They're just flying around through the galaxy, just like stars orbit around in the galaxy. These planets themselves are not directly orbiting stars. They're just moving through the galaxy. So how could we possibly detect this? So the question I want to ask you is, which of our techniques, Doppler shift transits, microlensing, or direct imaging, do you think can be used to detect free-floating planets, planets that are orphans in the sense of not orbiting around stars? Is it Doppler shift transits, microlensing, direct imaging? So talk for a second about this. It could also be there's a guess in the front that it's a trick question and it's one of these, none of the answers. That's, of course, a possibility. Okay, so if you think the answer is Doppler shift, raise your piece of paper or your hand. If you think it's transits, piece of paper or hand. Okay, few. If you think it's lensing, raise your piece of paper or hand. Okay, a few more. Direct imaging. Okay. So the right answer is microlensing. Doppler shift and transits both require detecting the star and the effect of a planet orbiting around the star on the light from the star. And so neither of these can be used to find planets that are not orbiting stars. Direct imaging, in principle, could be used to find planets that aren't orbiting stars, but in practice it hasn't been. It's too challenging. The one that's actually been used is this microlensing technique. So in this version of the technique, these free-floating, orphan, lonely planets pass along the line of sight between us and a distant star, and they produce a short brightening in the light from the distant star. That happens even if this planet is not itself orbiting around a star. That works even for these free-floating orphan planets. And so that's actually the technique that's been used for this discovery. Yeah, that's a fabulous question. So the question is, how do we know it's not actually this picture where the planets are just orbiting far away? And so you don't necessarily see the nearby star, or the nearby star in quotes, is so far away that you don't really know if the planet's associated with it. That's actually a huge problem in the interpretation of these results. And so I think the honest answer is we're not 100% certain. Some fraction of them really could be just on very distant orbits. Yeah, great question. So if they are actually not orbiting around a star, how did they get there? So I want to show you a computer animation of how this might happen. In particular, we think that planets form around stars. They form in disks of dust and gas around stars. And so initially, at least, probably all planets, or the vast majority of planets, are actually orbiting around stars. So the question then becomes, if that's right, is how do they end up not orbiting around a star? And this is a computer animation based on actual numerical simulations. It shows 1, 2, 3 planets orbiting around a star. The planets kind of happily orbit around for decades and decades. Eventually, the planets in their orbits happen to get close enough to each other that the gravity of those two planets as they orbit close to each other, their mutual gravitational interaction, the gravitational pull and push that the two planets produce on each other is big enough that it kicks one of the planets out of the system. Okay, there it goes. Okay, leaving behind a star with just 2 planets orbiting around and now a freely floating planet. And this is an example where gravitational interactions among the planets can lead to the ejection of planets from the stellar system. We actually think that this exact process is what produces the Oort cloud of comets. So to remind you, our sun is orbited by this roughly spherical cloud of comets whose extend in distance basically out to the distance of nearby stars. These comets, we think, got there because early in the history of the solar system, comets orbiting around happened to get too close to Jupiter or Saturn, and the gravity of Jupiter or Saturn ejected the comet from the inner part of the solar system to the very outer solar system. So this process of close gravitational interactions actually has many effects on the properties of planetary systems, both ejecting planets potentially from the stellar systems, ejecting comets out into the Oort cloud. Okay. So what I want to turn to now is describing some of the surprises that we've learned by studying planets around other stellar systems. And to do that, I want to remind you of what we know about the solar system, what actually organized our thinking when we were trying to explain how the sun and the planets formed. Our goal was to explain these properties of the solar system. Planets have roughly circular orbits. Planets all go in roughly the same direction, and they orbit in the same plane. And the inner planets are rocky. The outer planets are more massive, and they have a different composition. They're less rocky. They're more made of gas and ice. And these different properties of the solar system really did, for the last 500 years, kind of define how we think solar systems formed and what we thought the properties of planetary systems were. And what we've now discovered, now that we've actually found thousands of planets around other stars, is that there are many stellar systems and planetary systems out there that have properties that are incredibly different from our own solar system. And so I want to first describe to you about how this hierarchy, the fact that the close-in planets are small, distant planets are big, is not unique. There are other planetary systems where that's not true, and then I'll turn to talking about a few of these other systems. So this shows an example of a bunch of planets around other stars. I made this plot about a year ago. We've discovered more planets now. In fact, we've discovered so many planets now that if I put them all on this plot, it just looks like a big mass of color and you can't really see anything. So I stuck with the kind of old version of the plot, which allows you to see some of the details. This is the mass of the planet. Big, massive planets up here, low-mass planets down here. This is orbital period, distant planets over here, close-in planets here. This is the orbit of Mercury. about 100 days. This is where the Earth sits in this plane. It weighs about 0.3% the mass of Jupiter. It has an orbital period of 365 days, so it sits about here. Jupiter sits about here, an orbital period of about a decade or so, a mass of about the mass of Jupiter. And all of these points are planets we found around other stars. So the first thing you'll notice that's really astonishing is that most of the planets we found around other stars are actually closer in than any planet in the solar system. Most of the dots are inside the orbit of Mercury. Does that mean that our solar system is unusual?
No, because isn't it just the more planets that we can see, and so they're closer to the sun, so using techniques they're easier to see?
That's right. So this is largely an observational limitation. Okay? It's because the primary techniques we use, transits and radial velocity, are sensitive to planets that are closer in. Okay? And in both cases, right, you need to see the planet orbit around multiple times to believe you've actually seen the planet. And so that biases you to closer in planets with shorter orbital periods. Exactly. And so this doesn't mean that planets like our own solar system are unusual. What it does mean, though, is that planets like our own solar system are not necessarily the norm. There are lots of planetary systems that are completely different from our own, where there are planets on orbits that are much closer in than anything in our solar system. The ones that were actually first discovered, and that really were a tremendous shock when they were discovered, are these up here that are known as the hot Jupiters. These are Jupiter mass planets, okay, Jupiter mass, but orbiting with orbital periods of a few to 10 days. And the reason these were incredibly surprising is that you cannot form a Jupiter mass planet at an orbital period of a few days. The reason is that all of the gas, the hydrogen and helium gas that makes up the planet, cannot be accreted, cannot be gathered up by the planet if the planet tries to form very close to the host star. It's too hot close to the star for the planet to actually form at this distance. So we think what's going on is that these Jupiter mass planets that are currently very close to their host star had to form very far away and then make their way closer to the star by some process. And so I want to show you one example of that process. This is a computer simulation. This is a disk of gas. This is a planet. The planet is orbiting around. You're not seeing the orbital motion. Okay, the planet is orbiting around. As time goes on, the Jupiter mass planet feels a frictional force due to moving through the gas disk. The gas disk out of which planets are forming is the orange stuff. The planet feels a frictional force that causes its orbit to slowly shrink in time. The dashed line is the radius of its initial orbit. As time goes on, the planet has moved closer and closer to the host star. And so this is an example of the kind of process whereby a planet can form in the outer part of the solar system, the stellar system, but as time goes on, it moves closer and closer to its host star, due in this case to a kind of frictional force that it feels by interacting with the surrounding gas disk. Okay? And so that's one way we think that you can produce these gas-rich, very massive planets close to their host star, where we don't think it's possible to directly form the planets where we see them today. And so this really was a huge surprise when this population of planets was discovered. There's another thing I want to emphasize about this movie. You notice these kind of rings of dark regions. The dark regions are regions where there's not very much gas. The brighter regions are regions where there is lots of gas. These dark ring-like features are produced by the gravity of the planet acting on the disk of gas. Those ring-like features that you see in this computer simulation should remind you a lot of this image of a star surrounded by a gas disk. So I showed this at the beginning of lecture a few weeks ago. This is actually a real astronomical image of a star surrounded by a gas disk. And in that gas disk, you see these dark rings, deficits of gas. And the leading interpretation is that those ring-like deficits of gas are produced by a process very much like what you see in this computer simulation, where the gravity of the planet acting on the surrounding gaseous disk kind of creates these deficits of gas that you see as the dark regions in this computer simulation and then in this actual image. So another bias that we had from our own solar system is that planets should have circular orbits. Most of the planets in our solar system have circular orbits, and so we inferred from that, since we have 8 examples of planets in our solar system, we inferred from that most planets should have circular orbits, and this turns out to be wrong. Here's an example of one of the many planets that we've discovered around another star, showing to scale the orbit of a planet around another star. This is the orbit of Mercury, Venus, and the Earth in their nice, beautiful circles. Here is the orbit of this other planet, which is incredibly stretched out, a very elongated elliptical orbit. That's one example. Here's again a plot of the eccentricity of the orbit, where if the number is large, that means the orbit is more stretched out, eccentric like this. If the number is small, close to 0, that means the orbit is relatively circular. Jupiter's eccentricity is the dashed line here. The Earth's eccentricity is also way down here. And so you can see these other planets around other stars are the points, the colored points. There are definitely some of them that have nearly circular orbits, but there's actually more of them that have relatively eccentric orbits. So it turns out that eccentric orbits are the norm rather than circular orbits. And this was also a huge surprise. We were biased by our own solar system into thinking that circular orbits were somehow common for planets, when they're, in fact, we now know that we've done the measurement, they're not common. So why are the planets' orbits eccentric? This computer simulation shows, again, these 2 planets. This is the same one I showed you before. The 2 planets orbiting around, their orbits are initially a little bit eccentric. As the 2 planets interact via gravity and the one gets thrown off out of the solar system, the other, through that process of gravitational interaction, kicking the one planet out of the stellar system, the other planet ends up with an orbit that's more eccentric than it started with. And so again, you can see that in the computer simulation. These are the initial orbits. They're more circular, relatively close to circular, a little bit eccentric. But as time goes on, as the planets interact via gravity, and one of the planets gets kicked out of the solar system, through that gravitational interaction, kicking one planet out of the solar system, the other planet is left with a more eccentric orbit. So this is one way of producing this population of relatively eccentric planets. It's not the only way. There's actually many ideas that have been proposed for how one gets eccentric orbits being the norm. And we don't know what the right answer is. This is very much an active area of research. The last surprise I wanted to mention to you is that in the solar system, there are not really planets between Earth and Neptune in size or mass. We have Mercury, Venus, Mars, which are a little bit less massive, or Mercury much less massive than the Earth. And then we have Uranus and Neptune, Jupiter and Saturn. By contrast, in many other planetary systems, what we find is that planets a little bit larger than the Earth turn out to be very common. And these have been dubbed super-Earths, a little bit larger than the size of the Earth. These show two examples of these super-Earths. These are obviously artist conceptions. We don't have beautiful pictures like this of these planetary systems. These two systems, this one has an orbital period of 122 days. This has an orbital period of a little less than 300 days. So these planets, right, are in many ways similar to the Earth. They're a little bit bigger than the Earth. They have orbital periods, though, that are only a little bit less than the orbital period of the Earth. One of the reasons these are particularly interesting is we've talked about sources of energy that can sustain planets being geologically active, having enough internal heat to generate tectonic activity, carbon cycles, volcanism, etc. And one of those ways of maintaining geologic activity is residual heat from when the planet formed. And just to remind you, what we learned in our understanding of the history of Mars versus the Earth is that larger planets that are rocky in particular are more effective at retaining their heat from formation. So they're in many ways more likely to be geologically and tectonically active. And so that makes these super-Earths extraordinarily interesting from the point of view of carbon cycles, habitability, things like that. Okay. So the last thing I want to do is try to synthesize what we've learned about other planetary systems, specifically in the context of how common are planets that might, in some way, shape, or form, be habitable. So before we get to the question I'm going to ask you, let me remind you that we know that there are many properties of stars and planets that affect habitability. The properties of the star affects habitability. If the star is really massive, it's extraordinarily bright, and it probably bakes any surrounding planet and boils any liquid water off. If the planet is too far from the host star, then in many cases the planet is probably frozen and can't have liquid water. So there is kind of a Goldilocks zone where you can have liquid water. For low-mass stars, the Goldilocks zone is closer in to the star than it is for higher-mass stars. That's just because the stars are fainter. So for a given star, you have to be closer in to be hot enough to have liquid water. I also want to remind you that we know that this story about the Goldilocks zone is very wrong, as the moons of Jupiter and Saturn taught us. They have liquid water out here at distances outside of this band. But this is one way of kind of shaping our thinking about habitability. So in this context, the question I want to ask you is which type of star, low-mass star, high-mass stars, or stars like the Sun, which type of star do you think it's easier to find a habitable planet around? And by habitable here, I really mean an Earth-like habitable planet, similar size, and a temperature where you can have liquid water. Is it stars less massive than the Sun, about the mass of the Sun, and masses larger than the Sun? And the emphasis on this question is easiest to detect with current techniques. So raise your hand or your colored piece of paper if you think it's easiest to detect Earth-like habitable planets around stars with masses a little bit less than the mass of the sun. Okay? About the mass of the sun? Few. Mass larger than the mass of the sun. Probably about equal guesses in each case. So the key to think about this question is to take this band seriously. And what this shows us is that for lower mass stars, Earth-like habitable planets are closer to the host star. Remember that our current techniques for detecting planets are biased to detecting planets close to the host star. Transits, radial velocity, Doppler shift. And so the ones that we're actually biased to detecting are stars a little bit less massive than the mass of the sun. We have, in fact, detected a number of planets now where the planets have sizes similar to the size of the Earth and have surface temperatures such that it's plausible that they have liquid water. These are two examples. This is one system, a star that's orbited by 5 planets. 2 of these planets, actually, these 2, shown in this Argus conception, have surface temperatures where we think it's plausible that they could have liquid water. And people have done a careful estimate of, given the number of stars that have been looked at and the number of planets with potentially habitable conditions that have been found, and something like 20% of stars less massive than the sun probably have planets that are rocky, so sizes similar to the Earth and made of rock, not gas, and have surface temperatures where you could have liquid water. So that's an amazing number. So remember, there are billions and billions of stars in our galaxy, and what this is saying is that of order 20% of them can plausibly host rocky planets with liquid water. That's a remarkable number. What about if we want to be a little more egocentric and are interested not in lower mass stars, stars like the sun? My colleague Jeff Marcy and a former UC Berkeley undergraduate, now graduate student, Eric Pettigora, did a study last year of how many planets as a function of size and temperature, really, has Kepler detected. Planets in this box are kind of Earth-like. They have surface temperatures similar to the temperature of the Earth and sizes similar to the size of the Earth. There aren't many planets in this box, but what they realized is that planets in this box are much harder to detect because they're fainter, they're smaller, and they're further away from their host star. When you correct for the difficulty of detecting these planets, they inferred that, again, about 20% of sun-like stars plausibly have Earth-like planets. So this 20% number is uncertain. It could be 3%, it could be 30%. But I think it's an inescapable conclusion that there are billions of Earth-like planets in our galaxy alone. So even if we take an extraordinarily narrow view of what it means for a planet to be habitable, and if we take the narrow view that that means it has to be a rocky planet with a surface temperature similar to the surface temperature of the Earth, we now know that there are billions of such planets in our own galaxy alone. Okay, so you look up at the night sky, something like 1 out of every 5 stars that you see plausibly has an Earth-sized planet that has a surface temperature that's roughly right for having liquid water. And that, I think, is, one of the most important results in thinking about our own origins and our own place in the universe over the last 40 or 50 years. And what that means, I think, is that this artist's conception of what a distant world might look like is probably not that uncommon. So what we're going to do next time is try to ask the question, given that Earth-like planets with roughly Earth-like temperatures are not that uncommon, how likely is it that there's life? So in the meantime, have a happy Thanksgiving. Anybody guess what this is? This is the Turkey Nebula. It's not actually a real nebula. This is a manufactured image that Charles found. But have a great Thanksgiving, and we'll see you next week.